Good morning, ladies and gentlemen. Welcome back to our third day of online training on HOMER software. We have already covered the foundations of HOMER software in the first 2 day session. Today we will be covering the last session of our foundations of HOMER software. Today's content of the presentation would be interconnected mini grid design, net metered PV system, feed-in tariffs, PV and storage for interconnected microgrids. So, ladies and gentlemen, you are most welcome to ask any questions or queries, clarify your queries from the expert at any time of the demonstration and in this 2 hour session. If you can post these questions to us, we can also ask them on your behalf from the experts. Moreover, the contents of the training, including the material and the presentations, are already available on SARC Energy Center's website. If you wish, you can also download those contents and go on with the exercise during the session or after the session at your leisure time. So with this, I may now invite Peter to continue with the session and start the today's session. Over to you, Peter.
Well, thank you. And I think we're going to start today with a PowerPoint. Was that your plan, Silver? Was to use that PowerPoint first?
Yes, Peter, that is to provide a background on how energy is metered, and because we're talking about grid-connected systems, we should understand how the utility measures electricity. So that is also to provide background on what would be the advantage of net metering and also understanding on feed-in tariff. Okay.
That's potentially confusing topic, so I'm glad you put that PowerPoint.
Yeah, so I'll fix this. So can you see my slides now?
Yes.
Yes.
Okay. Yeah, so good day everyone, and I want to show how net metering and feed-in tariff is processed by HOMER. So let's start with this simple diagram on the right with a connected load that's connected to the grid. So the utility would expect that a load would only consume, so any connections to the consumer would only have a single flow of energy from the grid to the load. Now, if we look closely, how the utilities would meter is they would put a meter and expecting that energy will only be consumed by the consumer. So metering will be expecting only consumption. Now, with the solar technology being cheap and affordable and can be easily integrated into the electrical systems, the metering system has to anticipate now import and export of energy from its load. So it experiences current flowing, energy flowing back, and aside from the energy being consumed by the consumer. So in this case, the meter, when it runs forward, as usual, the consumer consumes energy, and that's being billed by the utility. But under a net metering scheme, when the electricity exported, it's credited to the consumer. So we'll discuss how HOMER would look into this type of metering connection so that we can model the system properly. So when we use the net metering button on the HOMER software, it interprets that you have a single meter, that when you consume energy, it will move forward or have a positive value. And whenever energy is generated more than what the load can consume, it's exported back to the grid. So in this case, the meter reverses That's mostly on the mechanical side, and the count is reduced. That is to reduce the consumed energy. So uh, if the HOMER software is clicked with the net metering price, it interprets that at the end of the month or of the year, depending on your setting, HOMER looks into what will be the net value of that meter, and if the value of that meter is positive, that means you are a net importer of energy. It's multiplied to the grid power price. So that will be your bill for the end of the period, let's say every month. But if the solar PV is producing more than what the load is consuming, at the end of the month you will have a negative value on that meter. So it's the system is a net exporter, and that value is then multiplied to the grid net excess price. So in the table below, usually the utility have a different price for consumed energy. That's the grid power price. In this case, we're using 0.2 US dollars per kilowatt hour. And if you're a net exporter, they will only multiply 0.05 dollars per kilowatt hour for exported energy. So HOMER can model this system if you click on the net metering button here. So that's for net metering with single meter. You have comment, Peter?
Yeah, I'd like to show them that we're in the software where how to get to that.
Okay, you can share your screen so you can.
Well, in order, I think Hassan has to give me that. Oh, there we go. Yeah, there we go.
Is it okay now?
Yeah, hold on a sec. I have to get the right screen. There we go. Wait a minute. No, I got the wrong screen, but I'll fix that here. Okay. Whoops. There we go. So you can see HOMER. I hope I did that right.
Yes.
Is that what? Yeah. Okay. So I got to this screen by either clicking here on the well, let's go to the home page just so you can see. I can click here on the hook grid and it takes me to the grid, or I can go here to HOMER grid, will take me to the same place. And there's several, this is kind of a complicated screen, but if we just stick with the simple rates, here's the two power prices that Silver was talking about. And here's the checkbox he was talking about. So with net metering turned off, then hour by hour or minute by minute, for each time step, if you're exporting, you get the lower price. And if you're importing, you get the higher price. But with net metering turned on, then it instead of that being calculated each hour, it looks at either the whole month or maybe the whole year and says, on a monthly or annual basis, were you producing more than you consumed? So this allows you to, let's say in the daytime, the solar is producing a lot of power, but nobody's home, and you're not using that power. It's flowing back to the utility company. Without net metering, you're going to get a low price for that power that you're not using. But with net metering, you're getting credit for it at the higher retail price, unless you produce more than you consume, not just in that 1 hour, but for the whole month. And in your region, there's probably not as much seasonal variation as there is in the U.S. But in the U.S., many utilities let you sort of bank excess electricity from the summer and get credit for it during the winter when the solar is going to produce less. Every utility is different, so I'm not familiar with all the different rules within South Asia, but we do allow you look at it either use net metering either where they do this netting out procedure on a monthly basis or an annual basis. But net metering is a great deal for the consumer because very frequently you'll have excess power in the middle of the day that you'd like to use in the evening, and without net metering, you're getting credit at the low price. And if you notice, when net metering is clicked, it says net excess price. When net metering is not clicked, it's just the sellback price. So every kilowatt hour going back to the utility is at this price. But with it clicked, it's only the net excess that's at that lower price. I hope that was clear. And gee, we're going to pass it back and forth a little bit here. Can you pass it back to Silver?
Yes, I think so.
Oh, maybe I can do that. Oops. All right.
Now Silver can share the screen.
Yeah, can you see my screen now?
Yep.
Okay, so I'll maximize this. So thank you, Peter. So as explained, this is how Homer would interpret clicking on that net metering button. Now we go to the next configuration. So what if I uncheck that net metering button? So in this case, the exported energy is measured separately from the imported energy, as if two values are kept separate. So let's say in the middle of the day when the solar is producing a lot, your export meter is counting forward while your import meter stops. In the evening, when you consume more than what the solar can generate because there's no generation at night, your import meter is increasing while the export meter stops. So it's only one or the other operating at a given time, but the values are accumulated over the period. So let's say monthly or annually. So at the end of the period, let's say every month, the bill will be your reading on the import meter multiplied by the grid power price as shown by Peter earlier. In this case, it's 0.2. But your exported energy measured by your export meter is multiplied by the grid sell price. In this case, it's 0.5, and that's deducted from the net from the imported grid power price. So the net of these two values is your final bill at the end of the period, let's say monthly. So in this case, in some policy or jurisdictions, they call this grid price as also a feed-in tariff. So whenever you export energy, they have a special price for that exported energy until now it's less than the grid power price. But in the earlier days of solar energy, like the EEG law, the sellback price is higher than the grid price. That is to incentivize generation of solar or renewable energy. So this has to be distinct from the configuration with the net metering checked, so that you will have a separate reading for the imported and exported meter reading, and also the multiplier for the prices. So grid price for the imported and sellback price for the exported energy. Okay, I hope that is clear. Now we can go to the next type of system. So
Can I ask a question?
Yes.
Silveri?
Yes, please.
Yes. In case of Pakistan, what we have is that we have different tariffs from grid for different timings of the day. For example, we have peak hour timings. For peak hour timings, we have a higher price of electricity. For off-peak times, the electricity price is low. But when you are exporting the electricity to the grid, back to the grid through net metering, they always charge you as per the lowest price. They never charge you on the higher price. Of course, the higher price is in the evening, so you never export the units back in the evening. But that's how the configuration in Pakistan and most of the South Asian countries is. So could you just speak on from that perspective?
Yeah, we can show how to do that in Homer. Silver, do you want to do that, or do you want? I'd be happy to do that. If
You can do it, Peter. So let me share, and you can. So Asan, can you share back Peter's screen
Uh,
just to
your yes, would you like to share something?
yes,
Peter would like to share something.
Peter, I think now you can share.
yep. So this is slightly more a bit complicated. So you can see we're on this simple rates. Can you see my cursor, or did I?
Yes.
You can see my cursor. Okay. So we're on the simple rates here, but if we go to scheduled rates, there's a lot more capability here. As you can see, I'm not sure I want to talk about everything here, but if we go to rate definition, so we've defined a rate here that's 20 cents on when you're buying power, and 50 and 5 cents when you're exporting power. But if there's a plus button here, if we add a plus, then we can go and use this control over here on the right. So I'm going to assume, although you didn't say it, Hassan, and this might not be true, that this peak price is only on weekdays. That's true in most places. Might not be true everywhere, but and so let's say it's from 6 p.m. to 10 p.m. on weekdays. So you can see I've clicked over on the left the blue row, and now I'm going from 6. Whoops, I went off the screen. 6 to 10. So now I've got this. Well, actually I've done it backwards here. So let me edit this. The daytime rate's probably the low rate, and the evening rate is probably the high rate, right? But the sellback rate is the same regardless.
Yes.
And you can put as many rate periods as you want in here. And I've seen utilities that have like 5 or 6 different rates, rate periods, winter peak, summer peak, shoulder peak, off peak, some utilities I've seen get really complicated. So this is pretty handy. You can define your time of day rates here. You can define your seasonal rates. You can have as many as you want, and you can have like you were saying, the sellback is always at the low rate. Actually, this probably isn't exactly the way you described it, but I'm not sure what the numbers were for in your example. I'm tempted to show more here, or should Silver,
you
what do you
can
think?
proceed, Peter.
Should I
Yeah.
should I show more stuff? Okay.
Yes, I'm going to discuss that anyway, so you can do it. I would emphasize on the utility numbers here, like what you're doing now. Okay.
Okay. And we've tried to explain what to do here, step 1, step 2, step 3. Likewise, many utilities have demand charges, typically for commercial customers rather than for residential customers. But you can do the same thing where demand charges are dollars per kilowatt per month, and they're based on the peak consumption during that month. And every utility is different. Every country is probably different. Even within the U.S., places are different. Most utilities have a 15-minute demand interval, but some have 30 minutes, some have 60 minutes. If you have a 15-minute demand interval, you probably really should have 15-minute load data. But anyway, so let's say the demand charge in your a common one is like $15 per kilowatt per month. So, you know, if you use 1,000 kilowatt hours in a month, well, that's pretty small for a commercial entity. Let's say 10,000 kilowatt hours per month. On average, that's something like 14, I think, something like 14 kilowatt hours would be on the average if your consumption was constant. But of course, it's not. And so your peak might be 40 or 50 kilowatts. So let's say it's 50 kilowatts and it's $15 per kilowatt per month. You're going to get a charge of $15 times 50, $750 as your demand charge on top of the energy charge.
Yes.
And so we've set that to 15, and let's say the demand charge only applies for demands during that peak period. So you can do the same thing here. You can say it's only on weekdays. Whoops. Right. So then what I have to do is have a second period where it's 0. So that would be all week. It's 0. It's 0 the rest of the time. So I fill that in, and then I come back here and say, but on weekdays from 6 to 10. Now, some utilities, it doesn't matter when you set the demand, you're going to get charged for that. Some utilities only charge you the demand charge for your peak demand during a certain period. And again, they can have different demand charges for different rate periods, you know, time of day, and I've seen some really complicated utility tariffs, which I don't recommend. As the time of day actually is a great concept. You know, a little bit of complexity is good. So that's the demand charge. Now, to be honest, we created the other piece of software, HOMER Grid, which we're not going to really get into this week. That is really much better at managing demand charges. But this will at least get your charges correct. And as long as I'm at it here, let me explain the other tabs up here. We have well, emissions we've talked about before. This is for but the numbers you want to put in here are the emissions from the grid. So let's say your utility is 100% hydro, you wouldn't have any emissions. But if you're coal-fired, of course your emissions are going to be much higher. If you're using high sulfur coal, this number is going to be higher. So this is the average emissions on the grid from each, you know, that the resources on the grid are producing. And so every time you consume a kilowatt hour from the grid, you're responsible in a way for the emission, for these emissions. So that's what that one is. Reliability is really interesting. We have two different ways of looking at reliability. So you can have scheduled outages here. So the green is normal operation, but if I've seen many places where the you know, especially small villages, etc., they'll have a diesel generator, but it will just run in the evening. So the schedule outage, we'd set this up so, I don't know, so let's say it comes on at 5 o'clock. So it's out from, you know, all day until 5 p.m. and it turns off at 11, let's say. So now you can see the green here is the only time that the grid is operating. So that's for typical small diesel powered utilities. You know, we're seeing fewer and fewer of those these days, but that has been really common back when diesel was the only resource. It's very expensive to run a diesel 24 hours, especially if the load's low. So that's for small systems, we've used to see that quite often, and we still do see it actually. But then more common problem is just random outages. Well, actually, wait a minute, let me back up a little bit. I've also seen these scheduled outages when the utility just doesn't have enough resources, and it's not doing rolling blackouts on a random basis. It's like, okay, the commercial district always gets power during the daytime. The urban residential areas always get power in the evening, and then the rural areas get power in the middle of the night. So I've seen that. The rural areas are kind of getting a bad deal on that, but so that would be a scheduled outage as well. But a lot of times it's just random. So if it's random, how often does it happen? So let's say it happens twice a week, so that'd be 100 times a year. And how long is it out for? Well, on average, it's out for 4 hours. But and you can see Homer just stuck a bunch of random outages in there, and you can recalculate it if you don't like the pattern. But if you see these little black sections are the same length every day, which isn't really realistic. So we can put in some variability in there. So let's put in 50%. So now we have some short outages and we have some long outages. And so you can set this up to be realistic. And then we have this button here, which is kind of handy. We didn't talk about how you can have two loads. I mean, we set up an electric load, but you can actually set up two electric loads. So you can have like a critical load, and you want a non-critical load. And so if you're setting up a mini grid or microgrid or whatever, a backup power system to supply power when the grid is down, well, maybe it's not big enough to supply everything. You just want to supply the critical loads. So electric load 2 would be your non-critical loads. And then Homer would size the microgrid or the distributed power system to meet the critical loads on electric load number 1. But it would only serve the electric load number 2 when the grid was up. So that's an option that we give you. So that's how we do reliability in Homer. And Silver, I think I can make you presenter here. Yeah, here we go. So I'm going to pass it back to you, Silver. You sure you want to make? Yes, because you've got more on the PowerPoint, I believe, right?
Yeah. So thank you, Peter, for that input. I'll maximize my screen. Okay. So if the net metering tech box is not checked, as I mentioned earlier, it will have a separate metering for import and export energies. So just to touch on another issue on some utilities, that they don't allow export of energy from the consumers. So Homer can also model that. One is by setting a sellback price of 0, and also setting setting the model not to sell back electricity. I'll probably show that model. Just to continue on what Peter started. So if we look into the scheduled rates, we can look into the rate definition, and we can see here on the check box that there's a box on prohibit any grid sales. So you can click on this, so that Homer will not export energy to the grid whenever generation exceeds the consumption. So that's one way of uh, complying to that zero export requirement from the utility. Okay, so Homer can model that specific grid condition. And going back to the third, to another case, which we encountered on the early part of net metering, is this type of connection. Because utilities are expecting loads just to consume energy, and with the drop in the price of solar PV, and you can easily install it on your own, like do-it-yourself solar, it's very tempting to install that. And what happens is electricity can also go back to the grid when generation exceeds consumption. However, the meter only counts any energy as consumption. So I placed there, it's a unidirectional meter that whenever the system exports energy, it's actually being added to the bill, because the utility did not allow export of electricity and made an extra protection on the meter that whenever energy flows, regardless of if it's going out or going in, it's all considered as consumption. So just in case you have this type of system, Homer can model it by not checking this net metering tech box, and also treating the exported energy as a penalty. So since the meter is measuring it as consumption, you can put the sellback price as a negative value of the grid price, as if you're paying the utility twice. So that's a one condition that also happens. So if you're encountering such a condition, Homer can model that, and it will guide you through uh, the sizing of the PV system, that it will not in fact produce more than what you consume. So with the load profile of the load and solar radiation, Homer can help you size up the system that it will prevent you from being penalized by exporting energy.
So
So
that's
there are
a,
more. Yes.
sorry to interrupt, Silver, but that's a very bad deal. And I gather you've seen that in the Philippines. But one would hope that changes. That's you're paying the utility to take your power. That's just wrong.
Yes, but that's happening.
Yeah, hopefully it's not happening anywhere else besides the Philippines, but you never know. Maybe it is, but that's something that really the regulators should correct. That's just wrong.
Happening
Yeah, because
basically.
yeah,
Have
go ahead.
you seen that in other places?
Yep, it's there in some part of India as well, because the distributor does not actually, when the distributor does not want you to sell it back to the grid because maybe the grid is not able to handle it, or some complication on the distributor side, that point it's actually that the grid would like to penalize. But yeah, it's changing. We are getting more policies in this matter, because people are actually trying to have more rooftop solars or something like that. Even for wind also they are doing this. So in that case, people are like, the government is trying to bring in policies, but yeah, it is taking time.
I mean, if I was in a place where they had that policy, I would just have my inverter
Yes.
prevent, just make it so we never
So-
export, just don't export,
I just also, yes,
and-
I
and-
also
and-
wanted to give consent on Peter's comment that why wouldn't you change the settings of the inverter just to stop it for exporting back to the grid instead of paying the price for that?
Right, you would do that.
Generally people are doing the same, but yeah, but just in case the grid might have any issue because of getting back from the people, like from the consumer. So because the equipments are not actually able to handle that load flow from the other side, so in that case they're going to penalize it, just in case this does not happen and people actually take care of not sending it back.
There is an issue with protection devices. So if you're getting reverse flows, the utility may need to, redesign the circuit breakers, protection devices. But Hassan is totally right that you'd want an inverter that prevented that from happening. Right.
Just to add it up, we are normally in our inverters, in case of Pakistan, they have a provision of anti-islanding, which I think in most of the inverters do have this provision, that if the utility is going on with operation and maintenance, they wouldn't like the electricity move back to their lines. So there is a provision inverter which stops it from going backwards. So just comment.
Yeah, no, that's a really important safety thing that all inverters have. You can't buy an inverter without that. Well, I mean, actually, UL, the company that bought Homer, that's their business, is safety and setting those rules and testing, inspecting, and certifying that inverters actually do that. So it's possible somebody could have a homemade inverter somewhere, but really, in the U.S. and I'm thinking almost everywhere, I'm sure you can't sell an inverter that doesn't do that, because that's a safety hazard for sure.
So Peter and Silverio, can we move on to a few questions? We have a lot of questions right now.
Oh, good. Yeah, sure.
So we have a question from Stephen Gorgel. He's from Germany. His question is, my grid doesn't have the meter symbols between the grid and AC bus. How do you add them?
Homer doesn't show the meter, and Silver just put that in there to illustrate the point. Was he asking about Homer, or was because the utility undoubtedly has a meter, but Silver just drew that M in there, right, Silver?
Yeah, just added that for illustration, because net metering topic in Homer could be confusing, because net metering, the term net metering feed-in tariff would vary from jurisdiction to jurisdiction. So just to illustrate it in the diagram, I put the meter. So single meter, 2 meter.
People throw these terms around all the time, and they don't always mean the same, So we wanted to explain what we mean,
So it was probably just for the explanation. It does not have this type of a symbol in the software.
Right.
So we have a question from Syed Faizan Ali Shah. Please discuss regarding the simulation whether it is possible to simulate single phase and three phase net metering.
No, it doesn't. Homer doesn't distinguish between single phase and three phase. That's a whole. In the first day, I talked about the different stages of design, and three phase is a little more complicated, and it's important to balance the phases, etc. And that's kind of at the detailed design stage. I've definitely seen projects where they had to redesign the circuits, the load end to balance the phases. But that's not a Homer. That's more of a power flow, power engineering. That's final design kind of question.
We have the last question from Shakir Khatiri. Is tiered consumption pricing scheme incorporated in Homer?
Tiered pricing.
Yes.
Homer Grid does that. Sorry, Homer Pro does not do that, but Homer Grid does. So perhaps we could do another training in the future with Homer Grid if there's a lot of interest in grid connected projects and things like demand charge management, electric vehicle charging. Homer Grid is really better for that, and tiered pricing, more complex tariffs. Homer Grid has a much more complex tariffs.
We'll address the rest later.
Was that it for questions?
Yes, this was all. You can carry on.
Right.
Okay, so that's one illustration I've shown, as Needy confirmed that it's also in other jurisdiction that also happens. So the penalty sometimes is not regulatory, but more on the technical results of the distribution impact study. That means the grid can only take so much of the energy you can sell back because it was designed primarily to meet your demand, but not to accept higher currents more than what they designed the grid for. So it becomes a penalty. And we can set that in Homer. So I'll just go back to my Homer slide here. And you can set that that limit. Here you have the parameter sale capacity. So in this case, we can check our load, and our specific load has a peak demand of around 407 kilowatts. So probably the utility has designed that system only to carry that capacity plus of course some operating margin. And we can set, let's say, for that sale capacity, that means we cannot exceed the capacity on the grid designed for power going in, to let's say 500 kilowatts. So that is to set the maximum capacity we can export. So that's one way of also addressing the power limitation of what the grid can accept specific to our point of connection on the utility. Okay, so we can, if there's no question about the net metering connection, also tariff, we can look into how Homer would help us design the system in consideration to the type of net metering or feed-in tariff that our specific utilities are applying for our areas of projects.
So Silver, as long as you're on this page, I think it's worthwhile to mention, it's not in the curriculum, but I think it's worthwhile to mention that grid extension cost in the lower right there.
Yes, very good, Peter. So
that's
here, yes, on the lower right end, okay, we also have values for grid capital cost. This is for grid extension. So just in case you want to consider the cost of extending the grid, just in case there's no connection, because grid extension can be an added cost to your system. So let's say, what's the cost you want to recommend, Peter, per kilometer?
Oh, say $10,000 maybe.
Okay, so you can put here 10,000 US dollars per kilometer of grid. So it depends also if it's single phase or three phase, or also on the type of voltage. And you can set the distance from the last stopping point to the point of connection where you want the system to be installed, let's say 2 kilometers or so. You can also do sensitivities later on what will be the limits on the grid extension, that it makes sense to do standalone system versus grid connected. So that's again another topic, but it makes sense to have Homer consider that. So this will be an additional cost to your system if you're not connected to the grid and you want to consider grid extension. There's also another bullet point here, very specific to that grid extension issue. So we have here also, in this case, it's at $8,000 per kilometer, but we can put it there to be consistent on our previous entry. And aside from extending the grid, you also have to maintain that grid extension, maybe clearing of the lines from trees or other obstructions. And also, you have to consider the grid power just in case you want to consider the grid extension.
Actually, Silver, can I jump in?
Yes,
Because
Peter?
I think this is kind of confusing, and I made a note. We should change this because we're using the same term, grid extension, in two different ways here. So on the previous screen, it was just adding some cost to the system. And that screen, all it's doing is saying, okay, we have this system and it's going to cost this amount of money for the PV and everything else, but we want to add, we just want to add this cost in. On the other screen, if you press the radio button at the top that says grid extension, it's serving a very different purpose. And it's going to compare the cost of, so let's say you have an isolated village and you're trying to decide, should we put a mini grid in this village or should we extend the grid to this village? Well, if it's a really small village and it's really far away, clearly the mini grid's gonna be better. If it's a really large village and it's very close to the existing grid, probably the grid extension is gonna be better. And so an important question is, what's the break-even grid extension distance? What's the maximum distance from that existing grid that it's sensible to extend the grid to based on the size of this load? So if you click this button, grid extension up at the top there, HOMER is going to calculate this thing we call the break-even grid extension distance, which says if this load is more than that distance away, the mini grid is cheaper, and if it's less than that distance away, the grid extension is cheaper. So I think that's a really important function that you get to with this radio button here, because utilities are extending the grid. There's a lot of uneconomic grid extension going on all over the world because that's what, utilities know how to do that. They've been doing it for a long time. It's straightforward, but it's very expensive. And up until recently, mini grids weren't good enough, really, but now they are. But it's new and different. This is really helpful for figuring out, well, really, should we be extending the grid to this location or not? And it really depends. So that's one of the uses for HOMER.
And Peter, I would like to make a comment on your discussion, just to add it up on this one. In our South Asian countries, most of the time, the already grid power available in rural areas, the quality of power is so poor, the frequency variations are so low and high that people would, I think, prefer to go with the mini grid, which has a reliable power source, compared to the grid power, which is mostly not of the same quality. And then it happens that the equipments are burned out, and there are a lot of problems on this one. So just saying that, would it be possible that in the software it could compare the pros and cons of these both options, something like that, if you could do?
Well, we can model the unreliable grid and we can model the mini grid. It would be two separate runs, though, I guess. But it's interesting that you bring up that point, because I just reviewed a paper, a report, a pretty major report the World Bank's coming out with, so it's still in draft, on on that exact topic of, they call it undergrid, putting mini grids where the grid already exists, because for people that want higher reliability. And India was one of the, they had a couple of cases in India and a couple of cases in Nigeria, and they're different because the regulatory system is really different in the two places. But it's a really important topic and a pretty major report. I bet it's still a couple of months away from being ready to release. But I got a look at it, and there's a lot of good information there. And it's a very important. I think you're right. I think we're going to. That's one of the reasons I'm so excited about this whole sector, because I think that's really going to change things. I think we're going to see a lot more of that now as a way to get people highly reliable power. Sorry, my little soapbox. It's one of my favorite topics, really.
But just to add it up, in our case, we actually implemented a project in Afghanistan last year, in which we had implemented a 20 kilowatt solar system at the Ministry of Energy and Waters building. And the main problem which we come up with during the implementation of that project was that in Afghanistan, there are basically two sources of power coming from different locations. One power is from the hydropower source, and the other one is from the power imported from the neighboring countries. So from the neighboring country power, when it's coming to that area, the power is more stable. But in case of hydro, it is unstable. So at different times of the day, power sources are coming from different sources. So this was a bit of a problem over there. The power quality should be the same, and then we had a problem of implementing the inverter and the solar panel integrating with the grid and putting on the net metering system. So these type of problems we do suffer in our South Asian countries.
Right. No, it's all over the world. I mean, Afghanistan might have a bigger problem than most places, but really, you see this everywhere. You see almost everywhere. Yeah.
So can we just move on with 2-3 questions? They are somehow related to that discussion which we are going on. There's a question from Shehzadul Haq. Can we connect battery system and simulate it with net metering?
Absolutely.
We can do that. Sir Bhagya Ratna Tola from Nepal. Is it possible to design a transmission and distribution for a mini grid?
Well, not with Homer. Homer doesn't look at the transmission and distribution system. Sorry about that, but that's not what we do.
Another question from Asad Iftikhar. In addition to the current discussion, large industries have enough captive generation to operate in island mode. These themselves can be considered as micro mini grids. This is another avenue where Homer has been of particular use.
Right. Yes, absolutely. And those captive generation systems are, traditionally they've just been diesel or often combined heat and power though. And Homer can do combined heat and power. We weren't planning to show that. We might show that on the last, a little bit about that, how Homer models combined heat and power on the final day. But those are all great opportunities to add solar and batteries now that those are cost effective. So we're seeing that all over the world where people that we call that a behind the meter system, and seeing that all over the world where large industries are, tea plantations and mines are good applications like that. Yeah, all kinds of things, right? Any other questions? No?
No, thank you. We are good with it.
So we're breaking up your presentation, but it's probably good.
Yeah, at least we can focus more on the issues, more pressing issues. So we have a background on how Homer would model those conditions, so it's more relevant for us. So for our modeling, I'll start with a simple model. So it's also in the manual that we have. Here, I'm modeling a system in Australia, and then we have a commercial load that has a peak of 407 kilowatts. So if we remove the solar for a while and click on the consumption, maybe we have to set back the simple tariff. So that's 20 cents per consumed energy, and for export it will be 5 cents. So there's no net metering yet, so we just calculate. So this is a typical baseline data we can have. So a load connected to the grid would expect this type of cash flow, just electric payments regularly on a monthly basis commonly. So you have here the grid, and that's the the net present cost is mostly based on the payment of electricity to the grid. Now, we can add a grid-tied system, particularly solar. So last time we modeled the solar as a component or solar array. But in this case, we wanted to model a PV system connected to the grid. So instead of connecting it to the DC side, we can have a PV system with an AC output. So HOMER can do that as a system. And of course, it includes all other costs like the inverters and racking system as part of a PV system. So you can connect that on the AC bus. So in this case, we can price it at 3,000 US dollars, and replacement would be 2005, just a sample. And of course, that's only for a 1 kilowatt system. But if you want to take advantage of economies of scale, as mentioned by Peter yesterday, if I add another price point of 100 kilowatt system, instead of having to pay 30,000 300,000 US, I can only pay, let's say, 240, and replacement can be cheaper at 200,000. Now the all-in cost also goes down from 1,000 to 800, just to show economies of scale. As you can see here, our curves is also changing with the price points that we have provided. And again, the time frame is a 25-year time frame. So if we add PV, we should have already our solar radiation data. So we check on the resource, and just in case we don't have, we can download from the internet and see our resource. So this is specific for our site that we have defined in Australia. As you can see, the winter is in the middle of the year. It's in June. Okay, now we can simulate the system by clicking calculate button. If it does make sense to add PV. And by the way, I selected here HOMER optimizer so that HOMER can select which size of PV system will it recommend for this type of load, and of course in that specific area. So our winning combination for the result is a 303 kilowatt system, because we have initially set our grid capacity, not here, and this, we have opened the grid capacity using the simple rates. So the recommendation is a 303 kilowatt system, and with the blended energy sources of solar and the grid, our cost of energy dropped from 20 cents down to 16.6 cents, just by adding 300 kilowatt of solar. Okay, so if we look into our grid configuration, we are not using net metering in this case. But if we click on net metering, we will see if there will be changes in the sizing that HOMER will do. So from 300 kilowatts, we can now see that it's recommending a 618 kilowatts. So as Peter mentioned earlier, having net metering is a policy direction to encourage more renewables on the grid. So HOMER, based on the economics, recommended a higher or a larger capacity PV system because of net metering. Okay, so going more on the details of what HOMER did in the calculation of that. So here we have the cost summary. Of course, we have added a PV system, and then we can show the cash flow. So in this case, we have one major expense because our of the and then we can compare the economics. We can check how much is the economic benefit of that 618 kilowatt system. So as shown in the screen, simulated by HOMER, the return on investment is 7.3, internal rate of return is 10.3, and the simple payback is 8.86 years. But with the discounted payback, considering the interest rates and inflation, it's around 12.89 years. So that is with net metering. So that's the economic advantage of having net metering in your system. Okay, so again, if we go towards a more realistic modeling of the system, our capacity based on the load is 407 kilowatts. That's again, as we have discussed earlier, the design of the system feeding power to the load, and we may be limited to how much energy or kilowatt capacity we can export to the grid. So we can go back to the grid entry, and we can look into a more detailed input for our system. So we can utilize the 500 kilowatt we have put here as a limit to how much capacity we can export to the grid. And we can also still check on the net metering. And for now, we'll just remove this grid extension cost for our purpose because it's already connected to the grid anyway. And below you have interconnection charges, which we will use 0 for now, and standby charges because some utilities would include this. So for our other parameters like the rate definition, we can click here the same values, 20 cents for the consumed power and 5 cents for the exported power. For now, we will just allow the system to export energy, and but limited by our 500 kilowatt grid capacity. So we'll use the same price all over the week just to have a simple rate. The demand charge will set initially at 0 just to have a to see the impact of a limited capacity. Reliability will set it all 0, and emission will use the default values. So if we can click calculate, so from the initial 300, we have here still the 618 kilowatt as our system. So it will still show the same economics that we provided. Okay, so going back to the grid rate, and on the rate definition, we can, let's say, try if we're not allowed to sell back electricity, what will be the impact of our system, as we have seen before, but now with more detailed values using this type of parameters. From 618 kilowatts, HOMER recommended only 265 kilowatt of PV because we're not allowed to sell back electricity back to the grid. So how would that impact our investment on a smaller system? So we can compare economics and the ROI and the internal rate of return.
Silver, you might be on a different screen, or at least, or maybe go to webinar might be frozen or something. I don't think I'm seeing the same thing you're seeing.
Sorry. Oh, maybe it's
It's paused
whenever I
probably.
click, it goes back to a different. Okay, if I double click, can you see the other screen?
I
You
don't
still
think
looking
so.
at-
No, no.
No,
Oh, thank you for
it's
telling me that because.
There we go. There we go.
Oh, can you see the screen now? The second screen?
We're looking at the simulation results, right?
Correct. Thank you.
Yeah.
Because it made lag a bit showing the second screen. Okay, now I'll check on the compare economic screen. If you can see, the difference is really not that far in terms of investment on that smaller system. But in general, what is an ideal system under this condition that you're not allowed to sell back electricity is a smaller 265 kilowatt system compared to a net metering system that you're allowed to sell back, which is 618 kilowatts. Okay, so that's the impact of not allowing to sell back electricity. Any comment from you, Peter?
And I think that was good.
All right. Okay. Let's see. Just look into the references. So there was a mention of having storage. Do you want us? So if we're not selling, we might as well store energy and use it when we have when there's no solar anymore, and you can use the stored energy uh, by using batteries. Okay, so what if we add storage battery? We can use lithium batteries then. Okay, and instead of a 6-volt battery, we can use a 48-volt system. So that's roughly 8 in series. So that's one battery bank that we have, and we can use the default values for the other part. We'll have you a HOMER help us design that system, but we need an inverter so that you can charge the battery and sell back electricity. So again, we can add here a converter, but in this case, we can use a generic free inverter. And HOMER will just use this 99%, 99 kilowatt, 99,000 kilowatts, so unlimited capacity. So if we click on the simulation, for this current condition, the adding the inverter and the battery does not provide a an advantage because of the parameters we set. Okay, so as you can see, because one probably of because of the load profile, that when the solar charges during the day, it's better to utilize that energy than to store it in the battery under the price that we have provided.
So, is it because the load requirement during night time is very low?
Yes, that's one. This is a commercial load, so there's not much demand in the evening. So storing energy will not really make an advantage. But that's a very good point, because you have found that the load profile does not provide an advantage in storing energy. What if we change the load profile by selecting a residential load with load shape with the same capacity of 2422 kilowatt hours per day, uh, uh, using the same configuration. So what we can do is we can remove this load and let's say add just to have that shape, residential, okay? But we scale this up to 2422 kilowatts so that our energy will still be as large as the commercial system. So if we do calculate, uh, the difference is not that big yet, but it's still recommending a solar only without storage system, okay? Unless there's a really big difference in terms of tariff for import and export of electricity. And
Yes.
let's say if we allow the system to sell back to take advantage of the energy that is used less during the day and used more in the evening, there'll be a different configuration on the system. So
I think that the back rate is also very low. For example, it's I think 5 cents. It should be nearly like 10 to 12 cents. Shouldn't be that low.
okay, so yeah, so we can go back to the grid and increase the sensitivity. Let's say, what if we increase it to 10 cents or as 10 cents or as high as 1 point or 0.15 cents. We can check on the improvements on or the difference on how HOMER configures the system. Okay, so if the sellback rate is very low, then it's recommending a smaller system. As the sellback rate increases, you can see that the capacity is also increased. Even if we have set limit on the sellback, the system still provides a larger system capacity for the PV because it's only limiting what is being exported and not necessarily the generation. So you can see the variations on how much PV is recommended based on the parameters we set, particularly on the price.
हो गया?
Okay.
Yeah, so I'm sorry, Silver, did you do one where there was no sellback allowed, no grid sales allowed?
Okay,
With
we
the
will try
residential
this one. Okay, private grid sales. Okay, so all these values will not be relevant.
Yeah, so we'll get rid of them because it'll just slow things down.
Okay, so yeah, we'll just leave one just to have
Yeah.
something there. Okay, and private grid sales, so we can check how Homer would recommend the system size and configuration would be. So here, without selling back electricity, Homer recommends a smaller system of 170.
Well, because that's the batteries, but is this with the residential load shape?
Yes, this is with the residential load shape. Yeah, so with peaks in the evening.
Huh. You know, this would be a good time to maybe do a sensitivity on the cost of the battery.
Okay. All right. So let's look into what would be uh, the effect of cost on the battery. So again, here we have a sensitivity, and instead of values of the cost of the battery, we have multipliers. So one would be the same value. And what would you recommend, Peter, for the next values?
Oh, I don't
Cheaper?
know. We have $550 for yeah, those so try 0.75 and 0.5.
Yeah. So in this case, we're simulating what if the cost of battery drops. Okay. So we can do sensitivities on that, and we'll see if Homer would put more batteries if the cost of battery actually goes down. So here, look into the
Nope,
table. So
it still didn't. I'll be darned.
yeah, so so expect more a cheaper battery. We can look for a more cheaper battery. Let's say,
I'm wondering if we didn't leave some setting. If you put 0.1 in there, that would be a way to tell if we left some setting in the wrong, because we've been deviating from the syllabus a little bit.
all right, yeah. But if, sorry.
0.1, so if it doesn't work at 0.1, that means we've got to check something else there, that we've got we've got some parameters set wrong.
Yeah, I think we may have, even with the cheap battery, it's still not recommending to install batteries. Yeah.
Interesting.
So it could be, yeah, we have that limit.
Silverio, could you check? I'm not sure if we have put a lot of load on the system, but the battery capacity is too small. I don't know if you can check with that as well.
We have
Actually,
used the Homer to optimize, so we have not set the limit on the battery.
click the advanced tab there.
Yeah.
So it's limiting us to 379 kilowatt hours of battery, but it's not using all of those. That's actually is kind of a low limit, but interesting. Well, you know, if you didn't get results that surprised you, you wouldn't need a model, right? If the model always returned results that you expected, that means you do it yourself. You wouldn't need the software.
And it's probably also a good exercise for the participants.
Yes, yes.
Let's carry on.
It's good exercise for everyone. We keep on playing with this.
Yeah, that's the the beauty of having the model, because then you can change the parameter, but you have to keep track of the parameters that you change. One thing that I wanted to model before we actually added the battery is modeling the system that I mentioned, and need to confirm that
Silvan,
negative.
Can you
Yes,
check the grid properties once for me?
this one. Okay. Can you see it now? Yeah, and
The rate definition. Have we set in some prohibition on the price? Prohibit any grid sales? Do we want that?
okay.
Well, I thought that would make the batteries more cost effective. You know what actually is doing it? I looked at it on my is we've got a really high discount rate. We've got a 10% discount rate.
Okay, so that increases the yeah. So discount rate is here in the project's economics, and
no, you
yeah,
only got 8%. Well, huh? You and I don't have the same file, but yeah, try lowering that to 4% or something.
Yeah, kind of 4%, and we'll see. So lowering the discount rate would be biased towards high capital cost. So it will allow more investments initially, especially the batteries. Well, even the cheapest battery with the lowest investment doesn't really recommend the battery.
Huh.
We want to cheap. Do you want to? What if we use a different technology of battery? You think this will change?
You know, if you open the file the C4 file is what I'm looking at. Try to open that up.
Okay. Sure.
So Peter will quickly address 2-3 questions. One is from Dr. Tanveer Ahmed. In terms of load selection, does HOMER provide any help for system stability, especially for wind and solar energy?
That question could mean a lot of different things. So one thing that we do to have is HOMER will enforce an operating reserve so that there's always more capacity available in case the load's varying. System stability gets into lots of different issues. There's something called transient analysis, which is looking at phenomenon at the 1 second level, or like this, and HOMER won't do that, but HOMER does enforce an operating reserve, and we should get into that on the last day. That's part of our 5th day agenda, is to talk about operating reserves.
Okay, so we can address that thing in the last round. So I guess we also have a question from Ejaz Siddiqui about the recommending to organize a training on EV charging stations are coming up, and so I think you might be covering that portion, right, on the 5th day, this EV charging.
No, that's This training is for Homer Pro, which is
Mhm.
our flagship product. It's been around the longest, and it's EV charging is a specialty that we've put into a newer piece of software called Homer Grid. So that would be another. We could probably do a quick demo of it, but we weren't really planning to do a training of Homer Grid. I could do a quick demo of it if you wanted.
Yes, I think just a short, brief kind of a demo, thereby you can just introduce the participants to that as well.
Sure. Do we want to finish what we started here? Well, actually, you have to hit calculate, Silver.
That's finish this work.
Right. Well, maybe while that's calculating, I'll just give a quick demo. If you
good idea, Peter.
Yeah, if you
Because
put the
this takes a while with several sensitivities.
Yeah. So if you give me back the screen sharing.
Okay. There are few suggestions from the participants to Silverio's model. They are suggesting you may reduce the replacement cost, increase tariff rate. So these type of suggestions if the model, I don't know. Check it out.
Yeah, actually, it is true. We could link the two the sensitivity on the capital cost and the replacement cost. That's always a good idea. It's a little complicated, but that might be a good thing to show in a minute. But since I've got this floor, let me just do a quick view of Homer Grid. I'm going to do this really quickly, but you can see we have the same starting screen, which you can turn off, and lots of help capabilities. And we have the same click on a map capability. So we could go over here to South Asia. But it's a little more set up like a wizard, but a lot of things are really similar. The load's very similar. The utility is quite different. We have a we have a tariff database for the U.S. But if you're outside the U.S., you would use this tariff builder here. This is the simple one, and in a minute I'll show you the more complicated one. You have to go over here to the libraries. This little symbol is the library. Oh, which went on my other screen, sorry. Whoa, hold on a second. Here we go. So here we have an advanced tariff builder. I mean, there's a lot to this, so I'm just going to do it really quick. But here's we can develop really complicated tariffs if you want, including tiers, etc. So you can see here we has tiers. So somebody asked about tiers, so we can do that here through the library in Homer Grid. These pieces are the same. It'll look really familiar. We do have a way, actually in Homer Pro, we have this way too, to pull in output from PV-Syst or helioscope. So instead of Homer calculating, converting the solar resource into PV production, if you have PV production data from wherever you got it, or if you got it from PV-Syst or helioscope, we can just import that directly. These are all the same. Outages are a little different. This reliability screen is the same. I mean, it's set up a little differently, but it's the same idea. But in the US, we're really worried about something we call resilience. So instead of frequent short outages, resilience is infrequent but long outages. You know, we have these hurricanes that come through and the power goes out for a week over an extended period, and it's a real problem. And backup generators aren't good enough because the roads are a mess, and if you've got it's over a whole region, there aren't enough fuel trucks to keep all the diesel generators running. So resilience has become a huge topic here, probably all over the world, but especially where there's been wildfires and tornadoes and hurricanes. The weather's been a real problem lately. Anyway, so we have two different ways of talking about reliability. This is for infrequent but long outages. And then what and we also have demand response and various kinds of incentives, combined heat and power, that's in HOMER Pro. But here's the EV charging one station. So let's hit OK. And so we can model the power requirements for an EV charging station. And so you have to just talk about, well, how much charging do you expect to happen? So you can have small vehicles, large vehicles, how many of them are going to come in, how much power are they going to need, how long are they going to be there for, et cetera. You know, you've got to set up this information for it. There's two different kinds of charging. There's what we call on-demand charging, and this is the idea: we have a charging station like on the highway, and it's like a gas station. People pull in and they want to get their battery charged right then and there. So, but more commonly is you'll have a charging station, let's say at your home or at your office. You've plugged in for 8 hours during the working day, or 15 hours at night at home or whatever. And HOMER will find the least cost time to charge the battery. So it'll look at whether there's excess solar available. It'll look at the tariff structure, and it doesn't need to be full power for the whole time it's plugged in. HOMER will figure out the most cost-effective timing to charge that battery. So those are very, very different algorithms, and HOMER can do either one or both. You could have both. So that's the EV charging capability. And then other stuff is kind of similar to HOMER Pro. The two biggest differences are three biggest differences: EV charging, demand charge management, and the complex tariffs, like the tiered rates. Those are the three big differences. So that's a super quick tour of HOMER Grid. And let me give this back to Silver.
So, Peter, this software which you mentioned, to my understanding, this is more for the commercial charging stations, right?
Yes.
On the utility scale. But what if the charging, they have a residential charging station for 1-2 vehicles for their own house? So should we continue with this exercise, or should we just put it into the load profile of the house, something?
Yeah, if you were modeling, you can model in a simpler way. You can model a charging station within HOMER in two ways. You could just modify the load profile. HOMER, we weren't planning to show this, but HOMER has a capability under the loads to what we call deferrable loads. Actually, Silver, I shouldn't have given it back to you so quickly. Maybe if you could click on load just to show this. So the C that has the third one there is deferrable load. That was originally designed for water pumping, where you have to meet the load, but you have a lot of flexibility about when you meet the load, because you can just store the water. You're pumping water into a tank, you're pulling water out of the tank, but you can pump when the power is cheap or when you have excess solar, and so it's much less. Actually, doing the deferrable really saves on your the amount of battery requirements you need for water pumping. But actually, charging an EV charging is kind of like water pumping, in that you got to meet the load, but you have some flexibility about when to meet the load, and that's what the deferrable load is all about. I wasn't really planning to give do a worked example of it, you can, because it was originally designed for water pumping, we thought the demand for water might be very seasonal. Like during the rainy season, you might not need as much water pumping. But in the dry season, you're irrigating, you need more water pumping. So we made it the demand for water be seasonal. Wasn't really planning to do a demo, a worked example of this. Actually, there's a lot of capability in HOMER, that we can't cover in just the 5 days.
Of course. So in case of water pumping, what we recommend that you can do it on any time of the day. You require 1-2 hours for a water pump to do the pumping. For the charging vehicles, I think it would be mostly during the night time, because then from the morning till evening the car is outside the home. So so my understanding is that charging should be put it manually into the load profile during the night time. But water pumping or ironing, these type of loads could be definitely just a comment.
Right. That is a good point. That if the car is not plugged in, you can't charge it. So that's a little different than the water pump. True. So
you can also put charging on load 2. That is just to distinguish it from your regular load.
yeah, right. And then you could do sensitivities separately. You could do a sensitivity on the EV charging and leaving the main load constant.
Yeah, you can see here, say EV charging. And you can have, let's say you want to charge it in the evening until early morning. So maybe the vehicle is already at home by 7 o'clock. So let's say if it's a small one, let's say it's a 10 kilowatt, you can have that sorry. Or you can shift that load.
Yeah, you just put the load
or early in the morning. Yeah.
Yeah. We have a Nissan Leaf. It's a small electric vehicle. And here in the US, it's just 110 volts. So it's only 1.5 kilowatts. So it charges all night for us, which works fine. But in most of the world, it's 220 volts, I think. So probably, I don't know in everywhere in South Asia if it's the same or not.
Yeah.
Yes, it's 220.
Yes. So you'd have
this is
more power.
Yeah. This is one way also of having that separate EV charging load, and you can specify which time. But in this case, it's a more programmed charging. And you can also have a different charging time for weekends and weekdays. Okay, that's also one way of modeling your EV charging. So we have here the 3 loads, and including the differable loads like water pumping or something else. Okay, so we can remove that for now. So going back to our model, what we're trying to do is to find a condition where it's it makes sense to store energy during the day and use it at night. And that also can happen if we have high tariff rates at night. So one way of doing that is we can have a rate definition. And if, let's say, we add a higher tariff at night, maybe as high as 30 cents. And we can define it in the evening. Then we can try if it makes sense to just remove the sensitivity first on the economics, because it could take some time. We'll have a cheap discount rate. So we'll see if it would prefer a there. So if the battery is really cheap, or yeah, then it makes sense to have storage. And also if the energy at night is expensive, so that's one condition that would favor the use of battery. So you can store energy during the day and use it when the tariffs are high at night. So these are different conditions that would prefer having the battery. Okay. Any other question?
Yes, Silverio, we have 2-3 questions. We have a question from Asad Iftikhar. Does Homer Pro allow for the automatic sizing of solar PV inverter when it's defined explicitly with the solar PV component on the AC bus?
Yeah, Peter.
Yeah, you want me to take that? Sure.
Yes.
You know, so you have to give me back the control. But yeah, there's a lot of capability that we've put behind an advanced button on the component pages. Here, let me screen and then move that out of the way. So let's go to the PV page here. Let me just show how this works. So just to make it easier to get started in Homer, we took a bunch of advanced parameters and we put them behind these advanced buttons. And so so you can explicitly model the inverter. So this is an AC. Let me stick that there. We've got the PV on the AC bus. So now it's calling it an inverter. If the PV was on the DC bus, it would be calling it a MPPT as a maximum power point tracker. Either way, it's the power electronic device that sits between the PV panel and the rest of the system. So if it's connected to the DC bus, you don't need an inverter because it's just going to the DC bus. I mean, you'll need an inverter over here. Now we don't draw these over here on the schematic, but they're so let me go back to your question, which was really about inverters. So we've got the PV on the AC bus. We're going to explicitly model the inverter, and we can, just to show everything on this screen, we can. And Silver mentioned this. If you're not explicitly modeling the inverter, then these power electronics devices that we're talking about need to be included in the PV, in the price of the PV. So each of the components, when we talk about the cost of the component, we're talking about the total installed cost not just the panels, but the racking and the wiring and shipping and installation and everything. This is what's the total installed cost. And if it's on the AC bus and you're not explicitly modeling the inverter, it's got to include the inverter. But if you are explicitly modeling the inverter, then you can put the cost of the inverter here and the lifetime of the inverter. And this is the this is the inverter that is on an AC coupled system. You've got an inverter between the PV panels and the DC bus, but you have another inverter between the DC bus and the load or the utility.
AC load. Yeah.
On a DC, I might be confusing myself. It's kind of late here. Anyway, you can optimize the size of that, and you can do it in one of two ways. By either explicitly putting, so this is the same sizing idea that we have over here. So we talked about that quite a bit yesterday and the day before. This is the same idea, but now it's for this inverter. And you can either do it based on its capacity in kilowatts, or what a lot of people in the industry do is something they call the DC-AC ratio. So as the PV size is changing, the inverter size is going to change with it. So especially the larger systems, they're now doing DC-AC ratios of like 80% or something. So the inverter isn't big enough to handle the peak PV output. But the truth is, if you've got a 2 megawatt PV array, it's not usually producing 2 megawatts. It's producing less than that. So you're sacrificing a little bit of PV output at noon on the sunniest day to save on the cost of the inverter. And people do that. So HOMER can do that optimization for you, and you can find out what is the optimum DC-AC ratio. It also has, as long as I'm describing this advanced tab here, this advanced screen, you can also, so for the simple inverter, we have a constant efficiency, but a lot of people are saying, well, that's not right. The efficiency depends on, so at 95%, at 100% out of its capacity, it's got a 95% efficiency. But at 75% of its, at 75% of its capacity, oh wow, I'm messing this up. Hold on, sorry. The efficiency drops down to 93%. I meant to put 95 up here. I don't know. 95.
Yeah, Peter will be covering that tomorrow.
Oh, we're going to cover that tomorrow? Oh,
Yeah.
Great. Sorry. Oh, yeah, you're right. Sorry, I'm getting carried away. Are we going to cover this stuff?
Solar.
Yeah.
And we're solar.
We're going to cover all this. Okay. Sorry. I should have just said that. That's for tomorrow.
Yeah. I mean, the plain answer will be yes, Hassan, for that question. So,
Okay.
as I mentioned, you can model the PV system on the AC bus, but HOMER gives you the option to play on the inverter within that system. So even the optimization, also including the parameters like the efficiency from full load to less load, HOMER can provide you that option to input the numbers.
Okay, thank you, Silvari. So you have anything more to cover, or should we address the 2-3 questions right now? We can cover them at the end.
Happy to do questions. Or Silver, is that okay? Or is there something else you wanted to?
Well, actually, what I'm also wanted to show is the negative tariff. But anyway, that's it's part of what we can cover. Like, remember this value here, for simple tariffs. And if like the conditions we mentioned with needy, like I'll remove this first. Uh, to have a pure grid system. And what if worst case is we have this kind of tariff that we're penalized for the excess? So how would the system respond to a regulation like this? So HOMER will still run, but will give you a size that will still provide some economics, but of limited capacity. So just give you the you know that HOMER can still model such type of grid that it will not let you, let's say, discourage you from exporting energy. So maybe that's one of the models I wanted to show. Okay, back to you, Peter.
Well, actually, Hassan, what were the questions?
Well, we have a question from Stephen from Germany. Does Homer Pro can implement grid services values like the value of frequency control from a battery storage, or would you just adjust the O&M price accordingly?
In Homer Pro, the way to do it would be to adjust the O&M price accordingly. The new version that is we're in testing now, in beta testing now, Homer Front. So we expect to release it probably in January. We'll handle that, and it's a issue that people are very concerned with for larger systems. It's not an issue so much for smaller systems, but so Homer Front is designed to do that, and we expect to release that in January.
Okay. We have a question from Shazad. Should we merge the solar with wind in an on-grid system?
I'm sorry, could you repeat that?
He's asking, should we merge solar with wind in an on-grid system?
Wind.
Well, you can model them both in Homer, and I guess we'll talk a little bit about. Were you planning to talk about wind tomorrow, Silver?
Yes, half of the time would be doing advanced solar, and the rest would be on wind.
Right. So Homer will model a solar system.
That's more on off-grid wind, but we can quickly include wind here if this system is. So we can, let's say, model a small 10 kilowatt
we
system.
Probably don't have time to actually run the model right now. But the simple answer is yes. You can include wind in any system or solar and combinations of the two. And one of the values of Homer is figuring out, well, does wind make sense, or should we just do solar? And wind's very sensitive to the resource. So doing a sensitivity analysis on the wind resource will tell you what how much wind do you need? How strong does the wind need to be for wind to be competitive with solar? But they sometimes complement each other really nicely.
Yes. And we are going to cover this solar and wind designs and their models in detail in tomorrow's session. So obviously participants can listen to detailed discussion on that one tomorrow.
Yes.
So I think we are over with the questions now. Do we have anything else to cover, or are we finished with it?
We're pretty much covered the sessions for today.
Okay.
Yeah, it's specifically more on the grid parameters, and also net metering and ideas on feed-in tariff.
So just a question, rather comment on this point. Right now in Pakistan, in our South Asian countries, India, Bangladesh, most of the inverters which are being imported are Chinese brands. and they are mostly people prefer to have hybrid inverter, which has a provision to install batteries with it instead of an on-grid inverter. So, do you have a provision of a hybrid inverter in this software, or do you have any specific manufacturers whose data is already uploaded in this software?
I think we have
Yeah.
Peter.
Well, Homer basically assumes that it is a hybrid inverter. That it's, you know, if you're modeling what's not a hybrid inverter, you just have to set the schematic up accordingly. But yeah, Homer can handle hybrid inverters is the simple answer. Yeah.
Okay. So if we are over with the questions and the time is almost over, so if there is no other comment, we can go on with the closing the today's session. Any comment from Peter, Silverio, Nidhi?
No, I'm good. It's funny in an in-person training, it's so much easier to tell if the audience is done or not, you know. But this is.
So I think we have already covered all the questions asked by the participant, and I would again repeat my earlier request to the participant that you may need to ask any question. Please be free to ask any question right in the chat box, and we will definitely address those with the speakers during the presentation and after the presentation. So now with this, I would just like to conclude today's session. We have already covered most of the things, almost all of the things which were in our today's agenda. Tomorrow we would have an advanced session on the wind and solar design, arrays, PV arrays, PowerPoint tracker, and dedicated inverters, wind data, turbine models, scheduled maintenance, and detailed modeling techniques. So with this, I may like to conclude today's session. Thank you everyone for attending the training. We had listened to some excellent presentations and discussions by our distinguished presenters such as Peter, Silverio, and Nidhi. All the presentations and the contents of the training are available on our website, sargenergy.org. We will meet tomorrow again at 10 o'clock Pakistan Standard Time. You can use the same web link to get connected for tomorrow's session. With me signing out, thank you again, all of you, for joining us today, and looking forward to see you tomorrow. Have a nice day. Bye-bye.
Yeah, bye now. See you tomorrow.
Thank you.